Hello students, welcome to this video. In this video, we will solve question number 331 to 340 of permutations and combinations. The link to download the PDF will be in description, and at the end I'll show you my website from where you can download all the books. So first we get 329 out of the way, which I said I had a brain fade moment in my previous video, so sincere apologies for that. So the question was 329 that find the number of times the digit 5 will be written when listing integers from 1 to 1000. So we had read the solution, okay? But the thing is that in this you should consider this 1 to 1000 in the form like 001, 002, 003 like that, okay? My confusion was that I did not consider that. Other than that, the solution is correct. The answer is also correct. Okay, so you can study this, right? So you see that the solution is correct here. 300 is indeed the answer. Okay, the other way to solve this problem is that between 1 to 1000 we have 10 digits. So at units position each digit will come 10 times, 100 times, sorry. 1000 by 10 is 100. Similarly, for tens and units place, each digit will come 100 times. So 100 plus 100 plus 100, that will be 300. That is the very simple, straightforward answer. This formula I have not shown, but yeah, I will probably show this formula in the next video. How do you derive this? And I'll put this in theory as well. Okay. So we continue with question 331. 331 says that let E is equal to left floor 1 by 3 plus 1 divided by 3 plus 1 divided by 50 right floor plus left floor 1 divided by 3 plus 2 divided by 50 right floor, and so on up to 50 terms. So the only changing thing is this 1, 2 and 3 up to 50 terms. Then find the exponent of 2 in E factorial. So it is the same formula which we are using. 1 by 3 is 0.33. So up to 1 by 3 plus 33 by 50, the terms will be 0. So E is equal to 17. Then we proceed like previous problem. Required answer is 17 by 2 left and right factorial plus 17 by 2 square and so on. So the answer is 8 plus 4 plus 2 plus 1, which will be equal to 15. Give me a moment. Yeah, all right. So after 34 you need to count it. Okay, 34 by 50 and 1 by 3 will be greater than 0. That will become 1. Now question number the 331 still relies on this formula. Okay, I will bring that formula in the next video. I'll add that in theory. Question 332 says that 3-digit numbers in which the middle one is a perfect square are formed using the digits 1 to 9. Find their sum. So the units place is 0 through 9, and tens place is 1 through 9, and the hundreds place is 1 through 9. There will be a total of 9 multiplied by 3 multiplied by 10, that is 270. There will be total number of 270 numbers. For each possible choice of tens place, there will be 90 numbers. For each choice of units place, there will be 27 numbers. And for each choice of hundreds place, there will be 30 numbers. So sum of these numbers is 27 multiplied by 100, and that you do 1 through 9. You add that. 90 into 10 multiplied by 1 plus 4 plus 9, and 30 multiplied by 1 plus 2 through 9, that is 135,450. I think I should explain it more. Okay, so let's reread the question. That what we have to do. So 3-digit number is there, middle one is a perfect square, and digits are 1 to 9. So since the middle digit, that is tens place, is a perfect square, it can be 149 only, and units place can be 0 to 9, and hundreds place is 1 to 9. So we have total of 270 choices. Okay, now for each choice of tens place, Okay, we fix this. There will be 9 multiplied by 10, that is 90 numbers for each choice of unit place. So we take this, so 10 goes out of the way, we have 27 numbers. And for each choice of hundreds place, that is these ones, we will have 30 numbers, 3 multiplied by 10, and that's how we have got this. Question C33 says that the integers from 1 to 1000 are written in order around the circle. Starting at 1, every 15th number is marked, 1, 16, 31, etc. This process is continued until a number is reached which has already been marked, then find all the unmarked numbers. Or rather, we have to find the number of unmarked numbers. So we start and we continue 1, 16, 31, we will reach 991. So the second round will begin at 6. So the numbers marked in second round will be 621 through 996. Then we will start at 11, so it will continue till 986. And in the next cycle we will have 1 and the cycle will repeat. So the numbers marked are 1, 6, 11, 16, 21. So numbers which leave remainder 1 when divided by 5. The number of marked numbers is 1000 by 5, that is 200. Question C34 says that let S be a set 1 through S. Find the number of subsets of A such that X in A and 2X in S implies that 2X in A. So partitioning S according to given condition, we have the following for A: 1, 2, 4, 8, 3, 6, 5, 10, 7, 9. Now for each of these, we have n plus 1 choices if n is the number of elements, because once we include a number, the larger one must be included. So total number of subset is 5 multiplied by 3 multiplied by 3 multiplied by 2 multiplied by 2, that is 180. Question number 335 says that prove that there are 2 multiplied by 2 to the power n minus 1 ways of dealing n distinct cards to 2 persons. The person may receive an equal number of cards and each one receiving at least 1 card. So each card can be dealt to 2 persons in 2 ways. Thus n cards can be dealt in 2 to the power n ways. However, in 2 ways, each person will receive no cards. Thus total number of ways of dealing cards in required manner is 2 to the power n minus 2, that is 2 multiplied by 2 to the power n minus 1 minus 1. Question 336 says that find the number of ways in which one or more letters can be selected from the letters A, B, B, C, D, E. So we can choose by picking 0A up to 7A. Sorry, this is the wrong question. 336 is this one. We can choose 0A to 4A, that is in 5 ways. Similarly, we can choose B in 4 ways. C, D, E in 2 ways. The total number of ways is 5 multiplied by 4 times 2 to the power 3, that is 160. However, in one of these cases, none of the letters will be selected. So the required answer is 160 minus 1, that is 159. Question 337 says that find the number of factors excluding 1 and the expression itself of the product of A to the power 7, B to the power 4, C cube, D, E, F, where A, B, C, D, E, F are all prime numbers. So we can pick the factor by picking 0A's up to 7A, that is in 8 ways. So A to the power 7, so it will be 8 ways. For B, it will be 5, and so on. So the total number of ways is 8 times 5 times 4 times 2 power 3, that is 1280. However, in one way all are selected and in another none is selected, factor 1 in this case. Thus required answer is 1280 minus 2, or 1278. Question 338 says that find the number of positive divisors of b1 to the power p1, b2 to the power p2 up to bn to the power pn, where b1, b2 through bn are prime numbers and p1, p2 through pn are positive integers. So like previous problem, bi can be chosen in pi plus 1 ways. Whatever the power is there, you add 1. So total number of positive divisors, including the number and 1 both, is, this is gamma function, which is product of all the elements. I is equal to n to I is equal to 1 to n pi plus 1. So what gamma function is, it will be p1 plus 1 times p2 plus 1 times P3 plus 1 times so on till Pn plus 1. So you put, it is the product. It is analogical, if you draw, it is analogical to sigma function where you add. So if it is a sigma function, it is P1 plus 1 plus P2 plus 1 plus P3 plus 1 and so on. So in gamma function, we just multiply them. Question 339 says that in how many ways we can select two unit square on an ordinary chessboard such that both square are neither in the same row nor in the same column. So first square can be selected in 64 ways. Once we have selected a square, we cannot choose from the same row column. Thus, the second square cannot be chosen from remaining rows, and 7 rows can be chosen from remaining 7 rows and 7 columns, that is 49 ways. So we have a total of 64 multiplied by 49, that is 3136. However, in choosing these squares, there are duplicates in the sense that squares are chosen twice. Thus, required answer is 3136 over 2, that is 1568. Now we come to the end of last question of this set. Find the number of pairings of a set of 2n elements. Example 1, 2, 3, 4, 5, 6, 1, 3, 2, 4, 5, 6 are two pairings of the set 1, 2, 3, 4, 5, 6. So we let A is equal to 1 to 3 through to 1. If we pick 1 as one of the elements of the pair, then the second can be obtained in 2n minus 1. Similarly, if we pick 2 as one of the elements, then the pair second can be obtained in 2n minus 3 ways. Okay, so 2 as 2n minus 3. Let me think. Okay, 1 is already paired with 2, so we cannot select 1 and 2. It should be 2n minus 2. Let me think a bit, okay? So suppose this is 2n, alright? If we pick 1, then we have 2n minus 1 elements, alright? If we pick 2, then 2 are already chosen. So we can pick the remaining 2 through 3 to 2n. So this should be 2n minus 2, right? So suppose we have picked up 2n elements, 2n minus 2 elements, we have made all the pairs. So 2n minus 1 will have 1 only. And if we pick 2 till 2n minus 3, for 2n minus 2 there will be 2. I'm not sure, it should be 2n minus 1 into 2n minus 2 into 2n minus 3 and so on. This should decrease by 1, not by 2. I will confirm this, okay? Again, I'm having brain fade moment. It is hard for me to solve while recording because I become self-conscious when I record the videos. So it would be either the answer. Let me think a bit for this. Second can be obtained in 2n minus 3 ways because 2 elements have been already chosen for first pair. Okay, so 2 elements mean 1 and 3, for example. Let's consider 1 to 3, okay? So if we consider numbers 1 to 3, 1 will have 2 pairs, 2 and 3. That is, 4 if we put 4, okay? So for 1, our 2n is here. So 4 means 2 into 2. So we take 1, 2, 3, 4. So for 1, it would be 2, 3, 4. So 3 pairs, that is 4 minus 1. Then for 2, it will be 2 sets, 3 and 4. 2, 3 and 2, 4 will be the answer, right? So that should be 2n minus 2. 2, 3 and 2, 4, right? 1, 2 you can't form. 1, 4 you can't. 1, 3, 1, 2, 1, 3, 1, 4 is formed. So now we can form 2, 3 and 2, 4. So it should be 2n minus 2. Okay, it shouldn't be 2n minus 3. No. I don't think. Let me look at the question again. Find the number of pairings of set of 2n elements or 2 pairings of the set 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 3, 2, 4, 5, 6. Okay, we have to find number of pairings, alright. We don't have to find the subsets. Okay. So in that case, the answer is correct. The answer is correct here. So for 1, we pick one number from the remaining sets. So that is 2n minus 1. Okay. Now 2 numbers are already picked, and then 2 is also there. So 3 numbers are gone. So we'll have 2n minus 3. The answer is correct. Yep, this is the answer. I was confused that about the question. Okay. So let me try to explain again. Okay. So once you pick a subset, you cannot pick that number again. So when you pair 1 with any number, you cannot pick that number for pairing with 2. So 2 numbers are gone, and then we have 2. So that is the third number gone. We will have 2 and minus 3 ways. Okay. So what this means is, if we are pairing 1, 2, 3, 4, for example, and you pair 1 with 3, then you can't pair 2 with 3. You can only pair 2 with 4. So the answer is correct. It took a bit of effort, but yeah. Let's see about the website, and astavaka.org. You come here and you can download algebra, trigonometry, coordinate geometry books. And fair piece of warning that there is a lot of typing mistakes. So take what is written with a grain of salt, and do not try to copy it. It won't work. Another thing is that very soon I am going to bring a question answer forum. I have developed it. I will have to just make sure there are no rough edges and do a bit of testing, and I'll bring it up. Once I bring it up, you can come and ask questions over there, and we can do things over there. We can eventually we will have chat as well. So we'll see. Okay. So with this, I will end the video here, and I hope that you are enjoying the playlist and finding the videos useful. So I thank you for watching the video, and we will meet again tomorrow with 10 more problems on permutation and combination. Till then, I will take my leave, and you should keep practicing and working hard. Once again, thanks a lot for watching the video, and we'll meet again tomorrow. Have a nice day.